Sound quality should be better. I'm actually using my XLR mic. We have deep space now. This video will probably be pretty quick because I just need to do some identity stuff. In a trig class, you'll be asked either to state identities or just know the trig identities or use the trig identities to show something is true. Probably the most renowned trig identity is going to be this one. I probably use this 10,000 times between all my classes. This is the Pythagorean identity, or you could just call it the main trig identity. You can prove it to yourself quickly just by using a part of the unit circle you already know, right? We know that this here at 45 is, now we're experts at this, so we know that that's this, cosine, sine. And so if we take our identity and we plug in this, our angle, then we're gonna have 45 degrees, right? And we just checked here, so we have a nice square root of 2 over 2 squared plus square root of 2 over 2 squared. And so this, you square both the numerator and the denominator when you square a fraction or a ratio, a rational number. So it's 2 over 4. That's 2 over 4. A half plus a half is 1. So we proved it to ourselves. 1 point usually isn't enough to prove something to yourself, so we can use this. What is it? X. If the x is long, that'll be right here at 30 degrees. Or this is also pi over 6. We know that the coordinates are 3 over 2 and 1/2. So sine squared, cosine squared, sine squared of pi over 6. We'll use the radians version this time. And cosine squared of the same angle is, here's my sine value, here's my cosine value. We'll check this, 1 over 4, because remember we're squaring this and we're squaring this. And this ends up being 3 over 4. Does that equal 1? Yes, it does. So that's the first trig identity. So that's one you'll use 1,000 times, and then in addition, other Pythagorean identities include this is true, and I believe this is simply, if you want to prove it to yourself, again, I like to prove it to myself in the margins because then I know that I can trust what I'm writing. Tan squared is the same as sine squared over cos squared. This comes from a reciprocal identities, I think they're referred to as, because these are all technically these are all identities as well. And so if I want to show myself that this is true, right, does this equal this, then I'll put this form of tan. A real quick aside is that I understand that when I say I'm going to show this, and so I'll just write the reciprocal identity, or the identity of tan squared being sine squared over cosine squared. You might think, well, if I was doing this, why would I think to just do that? And that is one of the harder things when you're learning math, is that the professor or the book or a lecture slide will say, so here in this identity, I'm just going to do sine over cosine means the same thing as tangent, so I'm going to use that identity. There's really no way to explain it other than the reason I just tried it right now is because honestly, I tried something else and I realized I was just making a more complicated problem. It wasn't clarifying anything, it was just making things harder. Keep that in mind when you come up against that. You see a professor that's like, all right, so we know tangent is sine over cosine, so I'm just going to write sine over cosine instead of tangent. Something that always got me was like, why would you do that? Why that and not a different identity? How do you know? And it's sort of just, you get used to the same problems showing up by glancing at the equality right here. That I know that secant is 1 over cosine, and this tangent is sine over cosine, and both of those have cosine in it. So I'm sort of going to try to make it work with this one and see where it leads, right? This is a YouTube lecture series, but if I was a professor, I would just probably show you the proof that the book does. The cleanest and the most serious, simple way to show something using this identity. The whole point of this YouTube channel is to do something other than what the professor is going to do in your class. So the aside is over, the tangent. I just wanted to be there for you because I've been there where you are. If you are that person that right now you're like, oh great, here we go with the, I'll just choose to show tan in this form. Why? Well, we'll get there. Anyway, see, and even for this, I don't know what I'm going to put there yet, so we're going to leave it blank. This, like I said, I know is 1 over cos squared theta. And so, is there something that equals 1 that makes this true? What if I just did this, right? Which we're allowed to do. Then we'll have, these have the same denominator, so then we can write this. And this is another identity, which you're allowed to use other identities to show that the identity you're working with right now is true. And so I'll write it a little more formally, but you probably don't need to do this. Since this is a true thing, then we can even write right here, Pythagorean identity. Since that's true, then this, so, okay, that's true. And then we can say, and therefore, so we're going to go to these problems. And, all right, this says the point on the unit circle that corresponds with a real number t. I'm going to tell you right now that the point of this problem is to show you that this all means it's teaching you how to be able to work with different arguments in the trig functions. So you have that. What else do we have? You'll see this. Right, it doesn't matter. The reason they're giving you this t problem is they're just switching out the variable to say, can they do it with this? If this is just whatever variable you happen to be working with on the problem you're looking at, due to how the problem was, say, arbitrarily labeled, right? So when you write down the problem or you make up a trig problem, you have the full liberty of actually using any symbol for an angle that you like. There are conventions that for certain applications, like if you have a certain physics problem or a certain engineering problem, you'll see the angle represented as that specific variable, but it can be any of those. Fine, sine. So some real number t, so this is p, I'm guessing they gave me p. Okay, well this is sort of we're doing the opposite of what I did in the last video, where we would take an angle and identify which x and y coordinates are right there. Whereas here we're just working backwards a little bit and saying, first way to identify this is to say, okay, I know my quadrants and we have a negative y, which is glaring at me and it's saying it's this over here. It's also positive x, I should say. So positive x, negative y means it's going to be found over here. I'll tell you that. And then again, the unit circle consists of these 3 points in each quadrant. It's broken up into those commonly. And this 3 over 2, I spoke about how it's the long one. So I remember they're not the same length as they are here. And it's not the short x, because remember this is my x. It's the long x. So I can assume that it's this one. This point on the unit circle is root 3 over 2 and negative 1/2. All right. What does it want me to do? It's just saying, first step of this is what is t? It's going to be negative 30 degrees will actually work here, negative pi over 6. But we'll sort of stick to convention and say we have pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7 pi over 6, 8 pi over 6, 9 pi over 6, 10 pi over 6.
And then our angle is 11 pi over 6.
That's t. And then, just to do sine of that number is the y value, which is negative 1/2. Cosine is the x value, which is root 3 over 2. Tangent is the y over the x, which is negative 1/2 over root 3 over 2, which is, use this space and then I'll erase it, is the same as this, which is multiplying across negative 2 over 2 root 3, which is a negative value where the 2's have canceled, and that leaves a 1 on the top and a root 3 on the bottom. That is my tangent, and cotangent is 1 over that, negative root 3 over 1, which is negative root 3. Secant, which is now, what did I say, this is 1 over cos, which is 2 over root 3. Cosecant, which is 1 over sine, which is negative 2. So the hard part there was just saying, oh my gosh, they put a t instead of a theta. And so for number 2 here, again, we'll do negative quadrant. That's down here. And look, the values are the same, which is this same length side triangle we like to call. Reference angle of 45 degrees. But what is it here? So
5 pi over 4 is my t.
And what I do then is we do sine of t. Sine of t is going to be, this is negative, this is negative. Sine of t is this y value, negative root 2 over 2. Cosine, the x value, tangent. I can quickly just glance and say it's going to be 1. If you want to write it out for yourself and see, I'm just going to say that any 45-degree reference angle is going to be...
The tangent function will either be 1 or negative 1, depending on the signs. Tangent equals 1, tangent equals negative 1, tangent equals 1, tangent equals negative 1.
And cotangent also equals 1. You know why? Secant is going to be 1 over cos. Cosecant is 1 over sine. So it's solved. All right, what's this next one say? The sine, cosine, cosecant, and secant functions have a period of blank. The tangent and cotangent functions have period blank. All right, I didn't show this, so I will do it now. So we normally look at this circle here. This is my x and my y. And so when you take one full trip around this circle, you continue to increase theta. You make the angle bigger and bigger, right, as you take a trip around the circle doing that. What corresponds to the function sine of theta, the argument being theta, versus theta looks like this. It looks like that. Goes in both directions infinitely, but one period is shown here. Right? This is a period. It's the period for sine, right? And the parts that correspond in the circle to the sine of theta versus theta here, you'll have pieces like this is 90 degrees up here, also known as pi over 2, right? And you do that once, twice, all right? Then what you've done is this, right? Right. At each angle, what's sine going to be equal to? Sine of that angle going to be equal to? Well, you have sine equaling 1 here, which we can verify, right? We know is true because sine of 90 degrees is 1. The coordinates here are 0, 1. You've traveled 0 distance from the origin, and the unit circle, the length of this radius is 1. And then when you come back around, right, when you do this travel, you're seeing that this y, now your y is decreasing. So all these points in between, you have this point right here, where these are your coordinates, right? Your y value is this one. So you have these points in between. There's your 45, there's your 45, right? Here, here, those are here, here. So that's how the unit circle translates over. And I always remember that if we do cosine real quick, period of cosine, we'll do cosine real quick and say, if we're dealing with this blue thing, we go all the way around once. Well, then what we have is, it's easy to remember sort of how to differentiate these two, right? The cosine will start up here at 1 and end up at -1, whereas sine, if you remember, started at the origin, right there. Sine starts at the origin, cosine starts up here at 1, which it should, right? Because on the unit circle, starts at 1, goes down below, and ends at 1. And we know it's going to keep going. It's just a sine wave as well, shifted over. The cosine wave is just a sine wave that's nudged over this much. So you can quickly remember the sine looks like that. This is 0, 0. And cosine looks like that. That's 1. And it makes sense. It should work like that, right? Because here at 0, right, for cosine, at 0 degrees, we have 1 comma 0. So the cosine is 1. At 0 degrees here, this is 0 degrees or 0 pi. This is 90 degrees or pi over 2. We'll have this little point right here, -1. Sorry, that's just the y value. So this right here is pi, 180 degrees. So we're just doing this, right? We're doing this is this, this is this, and you always remember that this is pi, and cosine is -1 there, obviously. It's this distance of 1, but in the negative direction. So cosine is 1 here. Then cosine is 0 because x is neither left nor right. It's in the middle. It's 1 here. Then the x comes over here for this one. Then the x comes over here for -1. Then the x comes back. This is the oscillatory periodic motion. The x comes back, and at this point, we can say x is 0 again, or cosine or x is 0 at this pi, 3 pi over 2. And then we get all the way here, and then at this point, which is 2 pi, or 360 degrees, cosine is 1 again. There it is right there. Cosine is 1. So the period, the whole point of going through that was to be able to answer this question, which says, we'll see that this happens at 2 pi. It repeats again at 4 pi. You can go the other direction too if you want. The wave continues both directions to positive infinity and negative infinity. 0 pi is here. So you see you have these little complete cycles around. It continues to repeat like that. And the period of this function is 2 pi, one complete circle.
Or one cycle within this wave repeats at 2 pi radians.
Period of cos is the same, right? So even though it starts at 1 here, a full cosine function is when you get back to here. So it's also 2 pi around.
And we have an entire video dedicated to graphing all 6 trig functions, which is coming up in this series. So for now, I will skip this demonstration of graphing tangent and let you know that one period of tangent is pi radians. As you can see, if you look at these blue arrows and notice the fact that the behavior of the function repeats at pi rather than 2 pi.
And we did all that because we wanted to answer this question, and we've pretty much answered it. We'll just do a quick table here. Function, period. Cosecant relies on sine, so it has a 2 pi period. So use the even odd properties to find the exact value. Even, odd. So all this is going over is for any function, if this is true, then the function is even. And if this is true, when you have a negative argument, it gives you the function, the negative of the function. If that's true, then function is odd, right? It is the case that sine is an odd function. Sine is odd, so sine of negative x is the same as negative sine of x, and cosine is even, so cosine of negative x is equal to cosine of x. The way to show that that's true and show why, we can draw this cosine function right here. So cosine goes like this, right, to positive infinity and negative infinity. It goes in both directions. This point is 1, and this is the cosine function. This is 1, this is -1. When you're looking at the function with respect to the origin here, this 0, 0 point, you'll see that this part mirrors this part, right?
What makes it even? Well, its symmetry about the y-axis does.
So this part mirrors this part, the rest of this mirrors it all the way to infinity, both sides. This whole part to infinity, this whole part to negative infinity. It just keeps going. So you have an origin. I'm not gonna be able to show you how big infinity is, but to help you think about it again, that's 1. It goes to infinity if you were to take that piece of it. So if you were to take this part all the way to infinity and this part all the way to infinity, it would actually be the case that subtracting the entire red part of the function from the entire blue part of the function leaves you with 0. Whereas sine of theta looks like this. You see how that's really bad? You see what's happening right here? When you're crossing the origin, the values of sine turn negative, right? So if you have this, all this, and now I say, let's subtract all the blue from the red, it's not going to be 0. It's going to be some leftover value. Use even odd properties to find the exact value of each expression. So what it means there is, sine of negative 60 degrees, sine is odd. Because of this is true. Sine of some negative argument is equal to
Negative sine with a positive theta argument, which we're much more comfortable working with.
sine of negative 60 degrees is the same as negative sine of 60 degrees. And the reason that's valuable is because we have really hammered down these points, 30, 45, 60. This is 1/2 root 3 over 2. Sine is root 3 over 2. So sine of negative 60 degrees equals negative root 3 over 2. Cosine of negative 30 degrees, cosine is even, which means cosine of negative 30 is the same as cosine of 30, which is known. Cosine of 30 degrees is this, 3 over 2 and 1/2. That cosine is root 3 over 2. So this is root 3 over 2. Tangent, you can look at the origin of our tangent plot here. I won't even redraw it. We'll just go there by observing our tangent plot, or from inspection, as they like to say, the math people. Just by inspecting the tangent plot, I can see this value is going positive, and then crossing the origin makes it go negative. So it's not even, because if it was even, it would do something over here. So it's odd. Tangent is also odd. That is helpful information, since we know, let's see, tangent odd, that means tangent of some negative of 30, all right, equals negative of just this. At 30 degrees, we have root 3 over 2, 1/2. So I want to say tan of 30 degrees equals 1 over 2 over root 3 over 2 equals 1 over root 3. I'm looking for negative tan of 30. So I'll just write this. So we have, therefore, tan of negative 30 degrees is negative 1 over root 3. Cool. All right, this one wants us to find trig functions, this point P. So I went over this in a previous video, but all those tips and tricks were about, you find this point on the circle and your coordinates are cosine, comma, sine. Well, now, since we're not working with the unit circle, we're venturing out to other circles of radius 5 and otherwise. So now, if we have this circle, or we have this circle radius 5, then these coordinates are the radius times cosine theta, and the radius times sine theta. And then here the radius is 5, here the radius is 5. I hope that makes sense of that. This point P is somewhere where that distance is 3. So I'm going to go out 3-ish positions here. Some 3-ish positions. And some negative 4 distance here. It's just saying this is negative 4, right? And then our lovely, lovely hypotenuse is going to be, thanks to Pythagorean theorem, spoilers, I already know this one. So 9 plus 16 equals 25, square root 25. So this is 5 here. That means our radius is 5. Now we're no longer working with the unit circle, right? Because this is not a unit 1, it's a 5. So now what we have to look at is our x value is r cos, our y value is r sine. Because remember, on the unit circle we were just using r equals 1. Well, now we have to do a little bit more work, and we know that, let's do sine. So r, which is 5, times sine of the theta is negative 4. So if we move this on over there, the sine of theta is negative 4 over 5. Another way of saying it is y over r. So cosine being x over r is this 3 over r, which is 3/5. Tangent they asked for is just y over x. There's no r involved. Y over x there. And they asked us for cosecant. It's 1 over sine. Sine, we determined, is negative 4 over 5. So flip it. And it wants secant, which is 1 over cos. Cos is 3 over 5, so our secant is 5 over 3. And then cotangents last, you just flip tangent. Easy. They want us to do the same thing with negative 2 and 3. So let's just do a quick triangle for Pythagorean's sake. If this is 2 and this is 3, then what is this? Well, 2 squared plus 3 squared equals 4 plus 9 equals 13. So that means that this would end up being root 13. So the radius of root 13, here's my r cosine, here's my r sine. That means root 13 times the cosine of theta equals negative 2. So cosine of theta is negative 2 over root 13. Again, the shortcut being sine is y over r, cosine is x over r, tangent is y over x, cotangent is x over y, is r over x, and cosecant is r over y. And to answer this one, cosine is right there, sine is y over r. Y over r is going to be 3 over root 13. Tangent is just going to be y over x, so 3 over negative 2. I'll write the negative over here. Secant is an r over x, cosecant r over y. And cotangent, we just flip the tangent. That's it. And let's see what this one wants. Use the fact that trig functions are periodic to find the exact value of each expression. No calculator. Okay, if I have sine of 390, well, sine of 360 is the same as sine of 0. So I go all the way around, and the value of sine is just going to go through all its values, come back, same here. Go through all its values, come back to this point, start again. So if this is 360 degrees, means this 360 degrees plus another 30 just has the values here. This is your sine right here. Sine of 390 degrees equals sine of 30 degrees, which equals 1/2. So when they say something, they probably don't expect this, but when they say something like use the fact that trig functions are periodic, I'm just tempted to say, look, I'm showing my professor why it makes sense what I did. Next one, same deal for cotangent 390. Just realized I picked two 390s in a row, but same trick, you're going here because you're going all the way around. It's inconsequential until you get to this last little bit, which is at 30. The cotangent of 390 is 1 over the tangent of 390, which, as we just discussed, is 1 over the tangent of 30 degrees, which is the y over the x. So the y over the x is this, which is, here you go.
Here I drew a box around 1 over root 3, but the final answer would be its reciprocal cotangent, which is just root 3.
And that's all I have for you. I hope it was somewhat insightful, and I'll see you in the next video.